two means of getting rid of the fuel are open to us. First, the fuel drain system. And second, a method of evaporating the remaining traces of fuel from the combustion chambers, the turbine, and the jet pipe. The fuel drain system utilizes the drain tubes which connect the lowest part of each chamber with the next chamber below it. Fuel remaining after a wet start will attempt to find its own level by flowing from the top of the engine to the bottom chamber. Once in the bottom chamber, the excess fuel exits the engine. Any remaining traces of fuel within the engine must be evaporated. To this end, the engine must be motored over on what is termed a blowout cycle. During a blowout cycle, the engine is turned over by using the starter motor. It's rotated for the time normally allocated to a full start cycle, but with the high-pressure fuel cock shut and the ignition system deselected. Air from the compressor will flow through the combustion chambers, the turbine, and the exhaust system, and assist in the evaporation of any fuel still remaining within. The tubo-annular combustion chamber system, shown here, is sometimes also called the cannular or can-annular system. The tubo-annular combustion chamber system differs from the multiple combustion chamber system insofar as it does not have individual air casings for each of the flame tubes. A number of flame tubes are fitted within an inner and an outer air casing, which makes this system a more compact unit. Notice the position of the igniter plug. This illustration is of a typical example of an annular combustion chamber system. It has only one flame tube, which is contained by an inner and outer air casing. The annular system has several advantages over the multiple combustion chamber system and the tubo-annular system from which it was developed. They are: for the same power output, the length of the annular chamber is only 75% that of a tubo-annular system of the same diameter. There are no flame propagation problems. Compared to a tubo-annular system, the air casing area is less. Consequently, less cooling air is required. The combustion efficiency is raised to the point where unburnt fuel is virtually eliminated, allowing the oxidization of carbon monoxide to non-toxic carbon dioxide. There is a much better pressure distribution of the gases impinging on the turbine, so it has a more even load placed upon it. We stated at the beginning of this lesson that we had to obtain the maximum heat release from burning the mixture of fuel and air in the combustion chambers. To do this, we must use the chemically correct air-fuel ratio of 15:1. Whereas in the piston engine the use of the chemically correct air-fuel ratio of 15:1 would cause detonation and dissociation to occur, in the gas turbine engine it poses no such problem, because there are no peaks of pressure to assist in their generation. The fuel and air are therefore mixed and burnt in the primary zone of the combustion chamber in the ratio of approximately 15 units of air to 1 unit of fuel by weight. The addition of secondary and tertiary air will, however, dilute the mixture, to the extent that the overall ratio may vary from between 45:1 to as weak as 130:1. In the introduction lesson, we stated that combustion theoretically occurs at a constant pressure. In fact, as is shown here, a small loss in pressure does in reality occur, as the gas passes from the compressor end of the combustion chamber to the turbine end. This loss of pressure is caused by having to provide adequate turbulence and mixing. Losses vary from 3 to 8% of the pressure at the entrance to the combustion chamber. During normal engine running conditions, combustion is self-supporting. The ignition system is actually switched off as soon as the engine has attained self-sustaining speed. Self-sustaining speed is the speed at which, after start, the engine can accelerate without the assistance of the starter motor. There may, however, be certain engine operating conditions which do require the use of the ignition system. For instance, just such a condition would occur following a flameout, which is extinction of the flame due to various unusual occurrences, such as the ingestion of large quantities of water thrown up from the nose wheels into the engine intakes during takeoff from a heavily contaminated runway. Combustion stability means smooth burning of the mixture, coupled with the ability to remain alight over a large range of air-fuel ratios and air-mass flows. This graph shows the limits of those air-fuel ratios and air-mass flows within which combustion will remain stable. The graph shows that combustion stability will occur only between a narrower and narrower range of air-fuel ratios as the air-mass flow through the engine increases. And beyond a certain level of air-mass flow, the flame is extinguished. Outside the ignition loop, which lies within the stable region, it is more difficult to start combustion than it is to sustain it once it has started. Restarting the engine in the air while it's windmilling is called a relight. A consequence of this is that, should the engine flame out at high speed or high altitude, it may be necessary to slow down and/or descend before the engine can be successfully relit. This graph illustrates a relight envelope for an imaginary engine, showing the flight conditions under which it would be guaranteed to relight if it was fully serviceable. The airflow through the engine will cause it to rotate or windmill, so the compressor is supplying sufficient air to support combustion. All that is then required is the opening of the high-pressure fuel cock to deliver a fuel supply, and operation of the ignition system to add the final ingredient, a spark. Operation of the ignition system to supply the spark is achieved by selection of the relight switch. The electrical power to the relight ignition circuit functions independently from that which feeds the normal start circuit. Combustion efficiency is the efficiency with which the combustor assembly extracts the potential heat actually contained in the fuel. This graph shows the combustion efficiency of a modern gas turbine engine across the range of air-fuel ratios which occur during normal operating conditions. Modern gas turbine engines have a very efficient combustion cycle. At high-power operating conditions, combustion efficiencies as great as 99% are achievable. And at idle, the systems will still give as much as 95%. The very high combustion efficiency attained in modern gas turbine engines is due in no small part to the fuel spray nozzles which are used in them. These nozzles have the task of atomizing or vaporizing the fuel to ensure that it is completely burnt. This is no easy undertaking, considering the velocity of the airstream from the compressor and the small distance available within the chamber for combustion to occur. Other difficulties occur as a result of the relatively low pressures attainable by the engine-driven high-pressure fuel pump at engine start. The pumps can be of the plunger type or the gear type. The pumps are fitted to the high-speed gearbox, which is driven by the high-pressure compressor shaft. The pumps are only rotating at a minimal speed during initial engine start, and are incapable at that speed of providing the high pressures, 1,500 to 2,000 pounds per square inch, required to give a good spray pattern. At engine start, when there is low engine RPM and low fuel pressure, the fuel spray pattern forms what is known as a bubble. This spray pattern is unable to atomize a fuel jet sufficiently for ignition to occur. As the engine accelerates during the start sequence, the pump rotates faster and builds up more pressure until the spray pattern forms a tulip shape. Atomization is still not sufficient to support combustion. Eventually the pump produces sufficient pressure to shorten the tulip until it touches the orifice. Only now is the fuel jet atomized sufficiently to ensure rapid burning. We've demonstrated then that a small orifice of fixed size will provide a finely atomized spray at high fuel pressures. However, when higher volume fuel flows are needed through larger bore nozzles, the pressures required from the pumps to provide that finely atomized spray become unattainable. Thus, for that type of situation, other methods must be found to sufficiently atomize the fuel at engine start when fuel pressures are low. The air spray system uses a high-velocity airstream to break up the flow of fuel. It requires only relatively low fuel pressures, and can therefore operate using the gear-type pump, which is much lighter than the more sophisticated plunger-type pump. The duplex system, and shown here the duple spray nozzle, effectively use an orifice of variable size. At low fuel pressures, a pressurizing valve closes off the main fuel feed to the nozzle, the only supply coming from the primary fuel line. The primary fuel line feeds the primary orifice, a relatively small hole, which is capable of providing a finely atomized spray at lower fuel pressures. When the engine accelerates during start, fuel pressure builds until the pressurizing valve starts to open. This allows fuel to flow through the main orifice, where it will supplement the spray of fuel from the primary orifice. In the vaporizing tube method, illustrated here, the fuel is sprayed from feed tubes into vaporizing tubes, which are positioned inside the flame tube. Primary air is fed into the flame tube through the fuel feed tube opening, and also through holes in the flame tube entry section. The fuel is turned through 180 degrees, and as the vaporizing tubes are heated by combustion, the fuel is vaporized before passing into the flame tube. This concludes the lesson on combustion chambers.